So for today's lecture, we will look into the spectral element method. And first, I will show you some slides. Again, more a motivational part about the spectral element method. And then we start with the theory part. And the theory part will use the little heat equation example that we have as the last homework. So the unsteady state heat diffusion equation. We will use that as our little example to start with the finite element method. But so first, let me try and show you and share this slide with you. And then hopefully you see the slides here about the spectral element method. So you see this part? So the spectral element method, it has been developed in computational fluid dynamics. You see here the seminal paper from Patera, who was the first to propose it basically in computational fluid dynamics. And when we start looking at the abstract of that paper, it pretty much summarizes what the method is intended for. So it's really about a method that combines, you see the first statement, combines the generality of the finite element method with the accuracy of spectral techniques. So we want to have the same flexibility like the finite element method, but then add an increased accuracy to it. And that really summarizes what the spectral element method is about. Let me see if I can admit this issue. And he was applying it to the Navier-Stokes equation in fluid dynamics, and initially started using different collocation points, these Chebyshev collocation points. We saw them mentioned from the pseudospectral method. He also uses these Chebyshev points together with the Lagrangian interpolations when he proposed this method. Now we will depart in that respect from this initial proposal from Patera. We don't use the Chebyshev collocation points. But we'll come to that later, hopefully today, to see what we mean by collocation points and what these point locations are actually. But so the application here was about fluid flow, fluid dynamics. That was interesting. The interesting problem they were focusing on. Now, this is still in use nowadays. So if you want to calculate fluid flow around an object, maybe a car or a Formula One racing car, or parts of it, then the spectral element method, for example, can be used for that. It's also used, for example, in climate modeling. So it went then to global meshes, and here you see, for example, this cubed sphere meshing as well. So when you take a cube and you kind of blow it up to a sphere, then you have still these 6 sides of the cube, which then kind of project onto the sphere. And that's a very useful gridding technique in order to grid a sphere. Otherwise, you have issues with the poles when you just use a latitude, longitude discretization. then you would have very small point differences, a very dense grid around the poles, and it coarsens out around the equator. So this cubed sphere meshing helps a little bit to even out the resolution of the grid. It doesn't have these pole issues. And then also for ocean modeling, for example, can be used. So you start meshing the oceans, and then you have also fluid dynamics, fluid modeling in the ocean that it can use. And then it was proposed at the late 90s for seismic wave propagation, and it has become a very popular method now to use in seismic wave propagation. One of the advantages is the free surface boundary. So we saw it with the finite element method. We can accommodate the free surface boundary very accurate because it's analytically correct how we can impose that free surface boundary. And this has a very well, it adapts well to surface wave propagation, which are the dominant waves when we look into seismic records. So the method is then highly accurate in how to describe surface wave propagation, for example. And that is one of the advantages why it was then becoming more and more popular, where finite differences method, they can be used very well for body waves. But then as soon as you have topography, a free surface boundary condition, then the spectral element method has quite a bit of advantages. So that's actually a simulation of such a regional or local simulation with surface waves. That's the one you see propagating outwards. And so it has become very popular to do this with the spectral element method. The same on global scales, but also important to have an accurate description of surface waves. Here, this would be just an event in Italy, which you see the surface waves propagating out and which dominate your seismic records. So if we can have a method which is very accurate in modeling these surface waves, then that's an advantage. And so in terms of softer codes, now there are quite a bit of packages now which use the spectral element method. So in fluid dynamics, for example, popular ones are these NEC 5000 or NEC box codes or Nectar++ library, which implement the spectral element method. In seismic wave propagation, so it started with these SpecFEM codes, initially developed by Dimitri Kometic and Jeroen Tromp. And so this has become quite a popular community code, SpecFEM codes, which comes in different flavors, 2D, 3D globe. But there are other packages as well, REXEM for regional spectral element method implementation, SES3D from Andreas Fichtner in Zurich, Salvus as well, developed in that group, which is a more recent code package. FESpec 3D, they all use the spectral element method. They implement that method and deal with seismic wave propagation. When it comes to books, I mentioned here 3 possible references that you can look into, which explain the spectral element method. You see the finite and spectral element methods with MATLAB and structural dynamics. They come more from an engineering perspective. And then if you're really interested in seismic wave modeling with spectral element methods, And for example, you have Andreas Fichtner's book about modeling and inversion, which is a good read to get into the details of the method. And then there's also I didn't mention that again, but the computational seismology from Heiner Eagle, for example, also has this spectral element method explained. Good. Let me stop here. So the method has really become very popular, especially for seismic wave propagation. And the goal today is start with its theory part, the introduction of it. So I want to start pretty much the same like we did for the finite element method. We will set up the weak form, the equation, and then look at the basis function. And the basis function, that's the point where the spectral element method then starts deviating from the finite element method that we looked so far into. So this is the main difference that I hope we can point out a bit today with the basis functions. I will do it again here on the whiteboard, if that works. You have the notes now, the PDF notes, which pretty much are what I'm putting down on the whiteboard. So you can really try and think through it rather than just write through it. Let's hope this works. Okay. Good. The first thing I want to mention is that so the method is a weak form method. So again, you can look into your notes. I pretty much have the same notes as the PDF that you have now. I just try and highlight these points which are important. So it's a weak form method. Oops. So it's it is a finite element method. You can see the spectral element method as a particular flavor of a finite element method, which tries and combine it with the spectral accuracy, so with a higher accuracy for the elements. So it's a weak form method like the finite element method. But the main difference differs in the choice of the basis function. And that's hopefully the part that we'll come to today. In the choice of basis function. Basis functions and the integration rule basically that we use together with that. So the use to interpolate the function. And the integration rule. So think of these 2 points where it differs. So one is first point are the basis function. So the spectral element method uses higher order polynomials, and there's in particular these polynomials that we take are the Lagrange polynomials. And the second point is this integration rule. So we use a specific, we come to that later, a specific integration rule to calculate these integral values over the reference element. So together with a specific integration rule, and this is also called the quadrature. So we'll have then a diagonal mass matrix. That mass matrix is mostly used for the wave propagation, but we can also think of the mass matrix when we look at the heat example, where it is the capacity matrix. So think of spectral element method as having Lagrange polynomials, higher order polynomials, and with this nice property of having a diagonal mass matrix, which is due to the polynomials that we use, plus then the specific integration rule. That's one of the main advantages. The other main advantage is the free surface boundary condition, which we can use, which we can model analytically correct, the spectral element method. So let's start with the weak form. And for that, we will start with our unsteady state heat diffusion equation as a little example. So the weak form is the first step in a finite element method or spectral element method. This is also called the variational statement. So let's start with this part. And for that, we look into our example, the 1D heat equation. And well, let me just write it. Here we would have Cv, then the time derivative of the temperature is equal to the derivatives of the conductivity times the derivative of the temperature. So do you remember how we call this equation when we don't use a force term? So there could be something like that, which we will ignore. So do you know how this equation is then called?
Half-space cooling system?
That's not the same. The half-space cooling model, that's kind of a derivation of this heat equation that we saw. Here, I mean the difference between homogeneous and inhomogeneous equation. So when we would have this plus F term, then we will call this an inhomogeneous equation. If we consider the force term as being 0, and we can ignore it, then this is a homogeneous equation. There's no forcing. It's basically determined by its initial condition. Think of the string. You have an initial displacement and then you just let it go. There's no additional force that we apply to it. The same here. So without the forcing term, it's just a homogeneous equation. So in our case, we have temperature T, which is a function of position and time. So this is the unsteady state heat equation we look at. And the domain here goes from 0 to L. CV, that's the specific heat capacity. Then we have rho, the density. And we have kappa, which would be the thermal conductivity. So CV, rho, kappa, they are material properties. So they can change from one material to another one. And we are interested in the temperature field. That's the one that we want to solve for. So let's just start with the weak form for this equation. Let's not bother too much about the initial condition and boundary condition right now. Do you still remember how we form the weak form, how we come to the variational statement? So there are two main steps. What would be the first step?
Multiply by the function W.
A test function, W,
Test
yes.
function.
What would be the second step?
Do the integration between this, within the, between 0 and L in this case, for example.
Right. Then we integrate over the physical domain, which is from 0 to L here. Good. So when we do that, we find the weak form. So we have the first term, first integral, W, our test function, time rho, C, let's just call C or C, well, doesn't matter, CV, time derivative of T, and then this is integrated from 0 to L, would be equal to the integral from 0 to L W, now the derivative of the right-hand side of kappa times derivative of T dx. Good, in principle that is already the weak form, but you see the right-hand side, we like to rewrite this part. And for that, we use the integration by parts. So when we do that, using integration by parts, then we have a minus integral of kappa times now the derivative of the test function times the derivative of the temperature field. And then plus the second term where we have the derivative over the whole expression, W times kappa times derivative of t dx. And this second term is why we do this integration by parts, since we have the integration of the derivative of this, which can be just evaluated at the integration boundaries. So we have W, the test function, times kappa times the derivative of the temperature, evaluated at the integral boundaries 0 and L. Good. Once we will set out the boundary conditions, you see that the boundary terms will come into this last term, basically. But that's it. That's the weak form of the 1D heat equation. So we wrote that down already. So let's come to the shape function. So we want to map from our physical domain to a reference domain. And this mapping needs a shape function. So what is the choice that we're doing here? Well, for these shape functions, we use just linear shape functions, like the ones we had in the finite element method. So let's start having our domain discretized. So we have 0 to L, and now we start discretizing it with elements. And let's say we have these locations for element E, goes from xe to xe plus 1, etc., etc. And so this is going to be mapped onto our reference element. So that's the mapping to a reference element, which goes from -1 to 1. Where we have then the coordinate xi. And here we use this shape functions n1 and 2. And here we have xi. So our discretization looks like the following. So we have the domain, say omega. That's the domain from 0 to L, which we are going to discretize into finite elements. So we can write this as the union of all the finite elements. With our elements omega E, which are defined in this range between the position xe and xe plus 1, corresponding there. So now we have it discretized into a number of finite elements. And so the mapping to the reference element, so we need to define what the reference element will be. So the reference element will have the coordinate xi, which we define to be between -1 and 1. And the mapping will be a linear mapping, just the same like in the finite element method, where we had position x. If we would go back now from the reference to the physical domain, x of xi will be using these shape functions, these linear shape functions NA. So we have NA of xi times xa, which is then, for example, we have N1 of xi times x1 plus N2 of xi x2, for example, for the first element. And here there is these shape functions N1 and N2. They are linear shape functions, and we can also call this as degree 1 Lagrange shape functions, because it's convenient for the -1, 1 range. So then we have these degree 1 Lagrange shape functions. N1 of xi is defined as this 1/2 1 minus xi. Then 2 of xi is 1/2 1 plus xi. So these are sometimes also called anchor shape functions. Where these nodal points, for example, xe plus 1, and in the reference element at -1 and 1, those are called the anchor points. Good. And using these linear shape functions, we find also the Jacobian. So J is the derivative of position x with respect to xi, which would be just this 1/2 of x2 minus x1. Good. So this should look all familiar so far from the finite element method. Now, where we differ now is we say these shape functions are really just for the mapping from the physical domain to a reference domain and back. So for that mapping, we just use low order shape functions, these linear shape functions. But now, once we are within our reference element, we use now higher order polynomials for the function approximation. And so that's the choice of the basis function that we come to now. And here we start differing from the finite element method. The finite element method would have used, for example, the same linear shape functions like we use for the mapping. Now in the spectral element method, we separate these two. So we have the shape functions, they deal with the geometrical shape of the problem. And now the basis function, they deal with the function expansion. So here we come now to the choice of the basis function. So far, so clear? No surprise yet. Weak form, shape function with the linear mapping. Now the basis function. And we mentioned it at the beginning. So here we're going to use these Lagrange polynomials, but higher order polynomials. So here in the spectral element method, the functions, they are expanded on higher order or higher order. Bless you.
Oh, my microphone is open. Sorry.
Yes, Lagrange polynomials. Keep it open.
Thank you.
Doesn't disturb. So let's look at the function f of x. And x itself is a function of position psi. And so we're going to approximate the function with a set of basis functions that go from 0 to n. And then we have the coefficients f alpha. And now these Lagrange polynomials, we write this as L alpha n of psi, and n will be the degree of the polynomials. So you're going to define what these polynomials are. So our Lagrange polynomials of degree n. And here is the definition of such a polynomial. So we can write this in terms of these products, psi minus psi 0, etc. Psi minus psi alpha minus 1 times psi minus psi alpha plus 1 to psi minus psi n divided by psi alpha minus psi 0, etc., etc. Now we have our psi alpha instead of psi. And what are these psi alpha? These are just the nodal points. With the nodal points psi alpha. And alpha goes from 0 to n for the degree n polynomial. And in particular, these nodal positions are the so-called Gauss-Lobato-Legendre point positions, or GLL positions. You see from 0 to n, it means we have n plus 1 of these points, of these nodal points. So are the n plus 1, and we call them Gauss Lobato-Legendre. Sometimes it's also switched. Sometimes it's called the Lobato-Gauss-Legendre points. But for us, the abbreviation will be GLL, Gauss-Lobato-Legendre, GLL points. And how do we find these point positions? Well, they are the roots of a characteristic equation. So the roots of the equation 1 minus xi square times now the Legendre polynomial, the derivative of it, xi is equal to 0. That's the characteristic equation. This equation will have the roots, and the roots are these GLL point positions. That's how you find these positions. So Pn here is the degree n Legendre polynomial. So that's a bit confusing at the beginning, but the basis function that we use are the Lagrange polynomials. And the Lagrange polynomials, they use a set of nodal points. And the nodal point positions, they can be found by this characteristic equation, looking for the roots of that. And this characteristic equation uses Legendre polynomials. So the easiest way is just to give you a little sketch of where these positions would be and how these polynomials would look like for our reference element. So our reference element goes from -1 to 1. And these nodal points, the GLL points, for a degree 4 polynomial, will have 5 points. The 2 endpoints, the one in the middle, 0. And then we have 2 additional points which are closer to the edges of the reference element. The position here for a degree 4 polynomials will be the square root of 3/7. And here just symmetric -3/7. That will be the actual nodal position of the GLL points. And then we have these polynomials. So green. So the first polynomial will be 1 at the first nodal point at -1, and then 0 at all the other nodal points. So the polynomial will look something like that. Goes down here, here, here. Then second polynomial would be 1 at the second GLL point and 0 everywhere else. So it will look something like this. Goes up here, comes down, and then 0 on the other one. Third one, do I have more colors? Yes. say third polynomial will be 1 at the third nodal point and 0 on all the others. So it will look something like that. Goes up here. Looks like that. And then the others are again just the same, but just symmetric. The last one would be so these are then the Lagrange polynomials. So this, for example, would be, you would have L0, 4, and we would have L1, 4, L2, 4, L3, 4, L4, 4. Those would be our Lagrange polynomials. And the nodal points here, these would be the GLL points. So psi alpha. So we would have psi 0, psi 1, psi 2, psi 3, psi 4. So is this clear? So the main point here is the function expansion, the top you see. So we expand our function onto these Lagrange polynomials. And we can set out the degree of the polynomial, let's say degree 4. And then we have these polynomials which are sketched out for the reference element. So we will have these n+1 polynomials and n+1 nodal points. And these nodal point positions, they are fixed by this characteristic equation with the Legendre polynomial. We look at the roots of that equation, and that determines what these psi alpha positions are for these polynomials. So if we set the degree, say degree 4, then we have the exact psi alpha positions determined, and we know what these Lagrange polynomials will be for the function expansion. This will be all set up basically by our choice that we do. And so the SEM method, the spectral-element method, it uses a high order polynomial for this function expansion. So let's say a degree 4 or higher for these expansions. Typically it's a degree 4 expansion. But obviously you can go as high as you want. So there are like two properties that are important. With these polynomials. So the first one is that our Lagrange polynomial, it's only one on its associated nodal point and zero on all the other nodal points. So the way to write this is we can say that the polynomial at nodal point beta, so L alpha, that's our Lagrange polynomial evaluated at the nodal point xi beta, is the same like delta alpha beta. So if alpha and beta are the same, this will be 1. If alpha and beta are different, this will be 0. It's one way of writing it.
Professor,
Yeah,
what is the meaning of delta alpha beta here?
that's a Kronecker symbol. So is 1 if alpha is equal to beta and 0 else. It's Kronecker delta. Have you seen this before?
I think it's in the FEM homework, right?
We had this before, yes. So it's called the Kronecker delta function. At some point, we also looked at the Levi-Civita alternating tensor, which was like an extension to 3 indices. The Kronecker delta only has 2 indices, alpha and beta, which it looks at. Levi-Civita tensor would have 3, looking at the permutation of those. But so this is the first property, and the second property, look at the function coefficients f alpha. If we go back to the expansion. So because the Lagrange polynomials are exactly 1 on each, on its associated nodal point. So if we're going to evaluate the function at a nodal point, f of x at xi alpha, one of the nodal points, this is going to be exactly the coefficient f alpha. So this will be f evaluated at xi alpha. We saw that last time a little bit with these degree of freedoms dA coefficients. If we're going to plot those exactly at the nodal points, then we can just plot the coefficient values. And here the same, because the Lagrange polynomials will be 1 and 0 everywhere else. Then these coefficients f alpha are just the function evaluated at that nodal point. So this will become handy when we look then at the, for example, the mass matrix expressions. And so what we're still missing is now this specific integration rule, the quadrature rule. So far we set out the basis function, but you see we will have these integrals that we need to evaluate on the reference elements. And for that we use a specific integration rule. So let's come to the integration rule. That we're going to use, and this is also called the quadrature. And so we use these GLL points as well for our quadrature. So the nodal points that we use for the Lagrange polynomials, we're also going to use it for our integration rule. So the spectral element method uses the same Gauss-Lobato-Legendre. And quadrature rule. Which means that the integral over the reference element, which goes from -1 to +1, of a function f of xi, and we integrate over d xi, is going to be approximated by the quadrature, and the quadrature here can be written as the sum from alpha to n over something with omega. These are coefficients of the function evaluated at that nodal point. These omega are called the integration weights. So you see the integral will not be evaluated analytically, but we approximate it by this sum of the function value at each nodal point times a weight. And these weights are then optimized such that the approximation will be as close as possible to the true integral value. And these weights can be determined as well, depending on the degree. We know what these weights should be. So for example, for a fourth order, the integration weights omega alpha fourth order expansion. So we will have the psi alpha position and its associated weight omega alpha. So then we have the position at 0 will have a weight which is 32 over 45. The position at plus minus square root of 3 over 7. Those will have these strange weights with 49/90. And the ones at plus and minus 1 will have a weight of 1/10. So these weights have been optimized such that then they approximate the integral value as close as possible using these nodal positions that we have from the GL element. So in principle, one can use here other quadrature rules. Not necessarily this one, which uses the Gauss-Lobachs-Legendre points, but we could use other points, Chebyshev collocation points, for example, which Patera was originally suggesting. So he was using a different quadrature rule in his initial spectral element method that he proposed. But we will see that when we use these GLR nodal point positions together with the Lagrange polynomials that we defined for the basis functions, this will now lead then to this diagonal mass matrix. And having a diagonal mass matrix is very convenient when we want to scale it up to very large systems. For the inverse of the mass matrix becomes trivial, and also to parallelize it becomes much more convenient because it stays then a local method. So how would that look then at the end? Well, then the integral starting in the physical domain. So this can be written as our integral from 0 to L of the function f of x dx. Will be same like over our domain omega. It's going to be the sum over all the elements of the integral over the finite elements, omega e, f of x dx. This is still in the physical domain. Just once we discretize the domain into finite elements, we can write this integral as the sum over each finite element integral. So now comes the complicated part. So each integral over the finite element, we're going to map this to the reference element. And so in the reference element, it goes from -1 to +1. Now we have the function of x of xi times the Jacobian of xi and integrate over the new coordinate xi in our reference domain. And now these integrals will be evaluated using this quadrature rule. So now comes the quadrature rule, which approximates this integral as the sum of this alpha using the quadrature weights, these integration weights, omega alpha. Then we have f of alpha because we saw that the function value at the nodal point, the GLL point, will be the coefficient f alpha times the Jacobian evaluated for that nodal point position, which we can call J alpha. Okay, so our integrals over the finite elements, they become then a sum over the alpha from 0 to n, and n is the degree of our polynomials that we chose. Or if you want, over the number of nodal points, the GLL points that we have. And then for each nodal point, we have an associated weight, an integration weight, omega alpha, and the function coefficient and the Jacobian for that nodal point position. Okay, let me quickly finish with giving you an example how this would look in 2D. So these, what we saw so far, are 1D integrals. So in 2D we have that the position x depends now on coordinates xi and eta, where we have our shape functions NA, which then depend on xi and eta times xa. They use 2D anchor functions now. So how would the integral look like that we have over our domain now in two dimensions? Would look like the sum over elements over our finite elements, which are not 2D elements. So think of, for example, a square or a rectangle. Now with these element points in 2 dimensions. So then we have quite a bit of GLL points. So these dots would be all the GLL points for a 2D element, for example, for a 4th order expansion. And so our integral over the finite element in 2D would then be the integral from -1 to +1, double integration of f of x of xi and eta times the Jacobian, which will also depend on xi and eta, times d xi times d eta. Good, and then comes the quadrature rule. It's going to be a double sum over alpha and beta. over the integration weights, alpha and beta, times the function coefficient evaluated at the nodal point alpha and alpha beta, which is associated to this. And the same with the Jacobian alpha beta. Good. Is it clear how it would look in 2D? And then you see how we could just expand this to 3D as well. We'd just add another dimension to it. And so we would have psi, eta, and then in 3D often there's gamma that would be used as the third direction in the reference domain. Okay, let's stop here for today. So the main point, what we saw is that the spectral element method, it differs in this part here with the basis functions. Before that, it was exactly the same like the finite element method, using the weak form, using low order shape functions for the geometry and the mapping to the reference element, but now uses higher order basis function for the function expansion. And then it uses this particular quadrature rule, the Gauss-Lebatto-Legendre quadrature, where we just approximate these integrals as a sum with weights of the function evaluated on these nodal points. And so then all these integrals, they just become these summations of the quadrature integration rule weight omega alpha times the function evaluated on the nodal points times the Jacobian. So what we come to next time is then we start setting out the system of linear equations. So what we want to come to is the matrix form for this method. Like what we did with the finite element method, we want to assemble these big matrices, the global stiffness matrix, mass matrix, and force vector. And then we can solve this as with a linear solver in matrix form. So we'll do that next time. For the spectral element method, it's going to be a bit tedious to write down these terms for the mass matrix, stiffness matrix. We'll have lots of these summations, double summation, triple summation, etc. So that's a bit the tedious part to write it down. But what we will see, especially for the mass matrix, is that the mass matrix becomes diagonal, and that's one of the main advantages of the method. So the main ingredients, we use Lagrange polynomials for the function expansion. Together with this GLL quadrature rule, then we will find that we have a diagonal mass matrix. And that's the whole magic, basically, of the spectral element method. So next time will be a bit tedious. We write these things out, but then you see how actually we come to that point, to these main conclusions. So do you have questions about that?
Professor,
Yeah?
is the mapping function here is linear?
Yes.
So I'm wondering what's the,
State functions.
so the only difference between FEM and SEM is the high order polynomials of the basis functions, right?
Right. Together with the quadrature rule. Yes. This is also specific for the spectral element method.
What about the third order polynomials?
If you want, you can use them as well. Yes.
But I'm wondering, it belongs to which?
It can belong to both.
Oh,
But here, what makes the spectral element method a spectral element method is this choice that you use Lagrange polynomials together with the GLL quadrature. Once you set this choice, it becomes a spectral element method. But you could use third order Lagrange polynomials here, or degree 2 polynomials, or even linear degree 1 polynomials if you like. And then you use it together with GLL points and this quadrature rule, and you will have a spectral element method. So it's just a particular flavor of a finite element method.
okay.
So think as these two as the main ingredients, which makes it a spectral element method. Lagrange polynomials and the GLL quadrature. And the rest now follows pretty much the finite element approach. But you see that this choice here is a very clever choice. The Lagrange polynomials with this quadrature rule, and especially with this property here, with this one, we can then simplify quite a bit how this mass matrix will look like. We will see that anything that is off diagonal will be zero because of this property. So the mass matrix just becomes a diagonal matrix. We come to that next time. So next lecture, we will actually write this out to just verify it. And then we can continue from there on with the linear system that we have in a matrix form. Is it clear? Good so far? Good. So it really just builds upon the finite element that we saw before that. Okay. So next time we see each other Thursday again. I would say try and finish the finite element homework for this unsteady state equation. Try and finish it by Thursday, and then we have our minds free for the spectral element implementations. Is it good? Good with everyone?
Professor,
Yes.
have we got the PDF of the SEM?
Yeah, we have it in the mail, no?
You
Yeah.
should have it by mail. I also put it on GitHub.
Okay, okay, Professor.
But you have these lecture notes then as well on GitHub. Yes.
Okay.
Good, and then I see if we can merge the recordings of these Zoom meetings with all these technical problems that we had. And let's see how that will look like. Good. Then wish you happy All Saints Day. And
You
then
too, thanks.
see you next Thursday.
See you.
Professor, bye everyone.
Bye
Bye.
everyone.
Bye, guys.